All right, thanks. So today we are going to talk about frequency response method. And since we are all electrical engineers, I'm sure it's not a news that in communications, radar, signal processing, as well as power electronics, most of the time the inputs that you are going to see is going to be a sinusoidal wave. So I have a system, let's say an RC circuit, and the input is going to be A sine omega t, and we are interested in knowing what the output is going to be. And once we understand the input output behavior of a system, we would then want to understand how to meet design specifications by designing an appropriate controller for that particular system. Okay? So typically such inputs are common in communication, signal processing, so audio, video, power electronics, and radar applications. Okay, so we have talked about step inputs for pretty much the entire semester so far, and step inputs are common in many other situations. So for instance, the first feedback controller governor, which was developed for steam engines by James Watt, it was meant to optimize the amount of steam that is entering the steam engine. Okay? And in that case, there was a step input in the sense that the person who's putting the coal into the steam engine, into that boiler, is actually giving a step input. So he puts certain amount of coal in the boiler. That's a step input to the boiler to start in producing more heat and generate more steam. And then the purpose of the governor was to actually control how much steam is actually entering into the steam engine. So that is the case where you have step inputs, but in communication you are always using certain frequency to communicate information, and usually those signals are represented by A sine omega t, where omega over 2 pi is the frequency. So in hertz. So when you have a 100 kilohertz signal, that means you have 2 pi into 100 kilohertz, kilo or 100 kilohertz implies omega equals to 2 pi into 10 raised to 5 radians per second. Okay? So you might have AM radio or FM radio or this audio processing, signal processing. So this audio that is going from here to the camera, all of this is taking input, a sinusoidal wave, and then producing certain output which is desirable, which has certain desirable properties. So that's why we are talking about frequency response now and moving away from the step responses that we have talked about so far. I'm going to assume that GS is stable. So all poles in left half plane or single pole at origin. the Laplace transform of A sine omega t is A omega over S square plus omega square. What would my y of s be? Gs A omega over S square plus omega square. Okay. Any questions so far? Straightforward. So this is the transfer function of the system. This is the Laplace transform of the input. So that's what the output is going to be. Now stability plus partial fraction implies that y of t is equal to A absolute value of gj omega sine omega t plus phi, where phi is angle of gj omega. Okay. Let us think about it. So my output has the amplitude of A multiplied by the absolute value of gj omega. So if the absolute value of gj omega is very, very high, my output is amplified. If my value of gj omega is very, very low, my output is suppressed. Okay. Let's think about a noise cancelling headphone. Okay, I see one right there. I'm sure many of you have used noise cancelling headphone. What's the purpose of a noise cancelling headphone? So let's say G of S is the transfer function between the external noise input and the output that goes into your ear. What should the value of gj omega be for audible frequencies? Omega between 20 hertz to 20,000 hertz. What would you ideally like gj omega to be? Small, very small. That's because for omega in 20 hertz, so 20 into 2 pi, and maybe 10,000 hertz. So you can hear, I mean, human ear can hear all the way up to 20,000 hertz, but I don't know whether so I know that for my own ears I have gotten the test done, so I can hear only up to 6,000 or 7,000 hertz. Okay, after that I cannot hear much. So different people have different levels of threshold for what frequencies they can hear, but there are people, I don't know who, but there may be people who can hear all the way up to 20,000 hertz. Okay, but for me the limit is 7,000, somewhere around 7,000 hertz. Okay, So for omega in this range, a noise cancelling headphone should have GJ omega close to 0. Okay. Similarly, in audio systems, you have bass and treble. And so if you are increasing the bass, you are increasing the absolute value of GJ omega for small frequencies, for frequencies close to 20 to 300 range. If you're increasing the treble, you are increasing the absolute value of GJ omega for higher frequencies. So this idea of designing a system which has certain properties at certain frequency ranges is very important. Actually, nowadays a lot of people are earning billions of dollars because of that reason. So you can count it. Bose, this particular audio company, it removes all the communication noise, so you can hear clear audio when you are listening it on YouTube. So this company is also doing something similar. Bose, Apple, who else? Oh, there are not many companies. Okay, maybe there are more companies that I cannot think of, but certainly many companies are working into audio processing or processing of audio signals in order to create nice audio experience for their customers. And it's all by appropriately picking the value of gain K and the phase angle phi at different values of frequencies. Okay. So this tells me that for a given system, this absolute value of GJ omega and the angle of GJ omega are important quantities, and we should be able to plot how they vary over the entire frequency spectrum. So all the way from 0.00001 hertz to 10 raised to 500, not 500, but 10 raised to 3 or 10 raised to 4 or 10 raised to 5 hertz. Okay. So let's look at one such plot, which is known as polar plot. This one plots on a complex plane the value of GJ omega. Okay. So you pick, let's say, so at omega equals to 0, you have GJ 0. Then at GJ 10, G of J 100, and so on. So you can plot this curve, and you can get, and this curve is known as a polar plot. So it tells you how the magnitude of GJ as well as the phase angle of GJ changes as omega goes from 0 to infinity. Okay. Let's look at an example of a simple RC circuit. So for this circuit, V out over Vn is given by 1 over R CS plus 1. Okay, so it's a first order system and it's also stable because RC is greater than 0. Okay, so what is G of j omega? It's 1 over RC j omega plus 1. I want to remove the denominator. I want the denominator to be a real number. So what should I do? 1 minus RC j omega over 1 plus r square c square. Right, so is this clear?
Shouldn't that be r squared c squared omega squared?
Oh yeah, of course, there should be an omega square in the denominator. Yeah, thank you. R square c square omega square. Yeah, that's right. Okay, let's plot this curve on the polar plot. Actually, this is the polar plot. But now, when omega is very, very small, the numerator is 1 and the denominator is 1. So this point is exactly 1. When omega is somewhat large, you have the real part is 1 over 1 plus r square c square omega square. The complex part is rc omega over blah blah blah. And you have a phase angle of gj omega, which is negative, right? Because this term is negative. So that's your gj10. So you have a phase angle. This is my angle of j omega, and that angle is negative. And as I increase the value of omega, I trace this semicircle, and when omega is very, very large, omega is close to infinity. So the real part is equal to 0, and then the imaginary part is also equal to 0 when omega is very, very large. And so you reach the origin when omega is large. So that's why gj infinity is at the origin. And this is the semicircle for the first order system. And this is known as a polar plot. So the purpose of polar plot is to know how the magnitude as well as the phase angle changes as you increase the value of omega from 0 to infinity. And sometimes they complete the polar plot by also considering negative values of omega. So in which case you will have something like this, and this is for negative g minus j omega. Okay, any questions so far? So we have studied two types of systems. So this is a first order system. We have a corresponding second order system too. And for second order system, you can also draw polar plot in a similar fashion. However, this is not the one that is commonly used in control system design. What is commonly used is Bode plot. And Bode is a fellow Buckeye. He was he completed his undergrad at OSU, I think in math around 1925, 27, so about 100 years back. And he developed he has made remarkable contribution on frequency response of control systems. And he was working on some early communication systems during the 1920s to 1940s era. So what is Bode plot? So Bode thought we should draw 20 log absolute value of Gj omega, and this is known as log gain function. And then angle of Gj omega, which is of course the phase angle, as a function of omega. Okay, so Bode plot. What would be the absolute value of log of Gj omega for this system? Let's compute it. RC j omega plus 1 minus 20 log 1 plus square root of 1 plus r square c square omega square. This is okay. So what happens when omega is very, very small? What happens to this number? What's the gain? Log gain at omega close to 0? Yeah, so this will be log 1, and log 1 is 0, so you actually have 0 gain or 0 log gain. So 0 at omega equals to 0. And usually this x-axis is in the log scale, log base 10 scale. So you have 0, 0.001, 0.01, 0.1, 1, and then 10, 100, and so on. Okay, so this x-axis is in the log scale. So for small values of omega, it's equal to 0, and for large values of omega, this function behaves as where should I write it? So for omega large, 20 log square root 1 plus r square c square omega square, or this is minus 20.
I had a question about the math.
Yeah.
So isn't that supposed to be this 20 log RCG omega plus 1?
Yes.
And then like the minus sign in the front because
yeah, because it's in the denominator.
I don't know, I'm just confused. I don't know where's my math, but like I just don't know how you jump from that to the square.
From this to this?
Yeah.
Okay, so because it's in the denominator, I can put a minus sign in front and take this to the numerator. And then what's the absolute value of 1 plus RC j omega?
Oh,
It's 1 plus r square c square omega square square root. Okay, so not very difficult. All right, so when omega is very, very large, I can neglect this term 1 here. So this is approximately equal to minus 10 log RC omega. Oh no, minus 20 log RC omega, because there is a square root here. So minus 20 RC omega, which is the same as minus 20 log RC minus 20 log omega. Okay, so at very large values of omega, of course this term would be small in comparison to 20 log omega, and this term will dominate this whole expression, and you will see that the curve actually goes down according to minus 20 log omega. So that's the slope of this curve is going to be minus 20, because our x-axis is log omega axis. Okay, so the slope is minus 20 dB per decade. Okay, so let me explain what dB per decade is. Okay, so 20 log absolute value of Gj omega, this is measured in decibels and in short form D capital B. Okay, so that explains the term minus 20 dB. What does it mean for per decade? Okay, so I want to explain what per decade means. So omega large implies 20 log absolute value of Gj omega is approximately equal to minus 20 log RC minus 20 log omega. And this is measured in dB. So if omega is large, is 10 omega large? Right? So 10 omega is large. This means 20 log absolute value of Gj 10 omega. What would it approximate to? So the first term doesn't depend on omega. So I'm going to write it as 20 log RC or minus 20 log RC minus 20 log 10 omega dB. Now the question is, can we simplify this expression? Oh, I haven't mentioned, but these are all log base 10, so it's not natural log. These are all log base 10. So knowing that these are all log base 10, what is log of 10 multiplied by omega? Just 1. And what about omega? So what is this term equal to? It's equal to log 10 plus log omega, right? Log of multiplication is sum of log. So I have log 10 plus log omega, and this is equal to 1. So what I have is, this is approximately equal to minus 20 log RC, which doesn't change, minus 20 log omega minus 20 dB. Okay. We are going to stare at this equation for some time and then try and make sense of this particular graph. Okay. So if omega is large, my absolute value of 20 log absolute value of gj omega is given by this expression. If I multiply omega to 10 omega, remember that this is omega scale, so I'm going from 1 to 10 or 10 to 100. If I do that, I see that my value on the decibel scale is going to be the same as the value at gj omega minus 20 dB. Okay? So the slope of this line going from 10 to, so if I go from 10 to 100, let's say this is my value at 10, this is my value at 100, and this difference is minus 20 dB, and this is a decade. Okay? A decade means I multiply the frequency by 10, and the slope is how much this reduces by given how much this increases by. So the reduction in y-axis versus the x-axis. So in x-axis I'm looking at 1 decade, at y-axis I'm seeing a reduction of minus 20 dB. So that's why the slope is minus 20 dB per decade. Okay? And that's a characteristic of a first order system. So whenever you have a first order system like this, you will always see this slope of minus 20 dB per decade. Okay, any questions so far? No? All right. Now I want to take you guys back to 1920s when you did not have a lot of sophisticated tools to figure out what the transfer function is. You didn't have any computers. And I give you a black box, and I don't tell you that the black box contains an RC circuit. All I tell you is that it has an input terminal and it has an output terminal. Okay? And I give you an oscilloscope so you can generate sinusoidal waves of any frequency from that oscilloscope. And I ask you the following question. I want to know what's there in that box. What kind of circuit, what kind of system is there in that, sitting in that particular box. My question is, given an oscilloscope which was available at that time, or a sinusoidal function generator which was available at that time, and given an unknown box, a circuit, can you plot this curve just by using these two items? You can? How would you do it?
Frequency sweep and then measure response.
So you will put in a sinusoidal wave of frequency 0.001. Well, I'm using frequency, but I'm really mean omega 0.001. You look at the gain of GJ omega. So let's say your input was sine of 0.001 t, and you look at the output. What's the amplitude of the output? And you plot the 20 log of the amplitude in this log scale graph. Okay, so you have a chart paper with this log scale, and you plot this. And you can do it for 0.001, you can do it for 0.01, you can do it for 0.1, and so on and so forth, all the way up to 100 or 1000, omega equals to 1000. And then you can draw a curve, and you can look at the slope of this curve. If you notice that the slope is minus 20 dB per decade, what does that imply? It's a system of this type. Okay? So in those days, being able to plot Bode plot was very easy because you had the hardware tools available to plot the Bode plot. And by looking at the slope, and at this point where the slope changes, so it changes from 0 to minus 20 dB per decade, you can actually identify what the value of this R multiplied by C is for that particular system. Okay? And that's why this plot became extremely useful at that particular point of time, because it was easy to plot this graph for a specific system. And using that graph, if you have enough experience, you can actually identify what kind of system transfer function you are actually looking at. And we will get to it in a bit, but I wanted to show you that this can actually be done here. Now this point at which you see a change in slope is known as corner frequency. Corner frequency. And the corner frequency is for this particular system, I think it is 1 over RC, but let me check. Yeah, 1 over RC. Now we haven't plotted the phase diagram, but we are going to get to the phase diagram now. Okay, so by looking at the gain diagram, log gain diagram, there are many things we notice. We notice the corner frequency at which the slope changes. The corner frequency for this particular system is 1 over RC. So that's where you see a change in slope. You see a asymptotic slope of minus 20 dB per decade. So this is for very high frequencies. And for very low frequencies, the gain in decibel is almost 0, or the log gain is almost 0 decibel. Okay? So that's the 3 things to remember from this log magnitude graph of the Bode plot. Now we look at the phase angle of the Bode plot. So let me erase this part. Angle of 1 over RC j omega plus 1, which is the same as angle of 1 minus RC j omega over what is the angle? Of this complex number? So I have A plus IB or A plus JB in this case. So what's the angle of a complex number? Imaginary part over real part. So that's RC omega minus RC omega over 1. Okay. So what happens when omega is very, very small? What's the phase angle? Omega is small, omega is close to 0. So what is tan inverse 0? 0. So when omega is close to 0, your phase angle is 0. What happens when omega is 1 over RC? So at the corner frequency, what happens to tan inverse? So my question is, at corner frequency, omega is 1 over RC. So what happens to tan inverse at corner frequency? Omega C. This is tan inverse minus 1. Anyone remembers what tan inverse minus 1 is? Yeah, minus 45 degrees. So at corner frequency, this is minus 45 degrees. So you reach here. What happens when omega is very, very large? You have tan inverse minus infinity. What is tan inverse minus infinity? Minus 90 degrees. So you converse to minus 90 degree. Okay. All right. So we have figured out that there is a phase change of 90 degrees at very high frequencies. There is almost negligible phase change at low frequencies, and around the corner frequencies there is a phase change of approximately 45 degrees. Okay, that is something we can read from the from this phase plot. Another important thing is that even the phase plot can be actually plotted using the input-output behavior of the system. Okay, so you can look at the oscilloscope of the output and you can figure out what the phase difference is between the input and the output, and that will also tell you what the phase of the system is it looks like. And one thing that we will study perhaps in the next class or next to next class, the change in the phase angle and the change in and the corner frequencies, they'll give you information about whether you have zeros. So how many? So the asymptotic slope is going to give you information about what the order of the transfer function is. So whether it's a first order transfer function, second order, third order, and so on. So first order transfer function will have an asymptotic slope of minus 20 dB per decade, as we have shown. Second order transfer function will have a slope of minus 40 dB per decade. Third order transfer function will have a slope of minus 60 dB per decade, and so on. So it will give you information about the order of the transfer function. It will give you information about how many zeros and where they are located, how many zeros are there and where they are located. And then by looking at the phase plot, you can actually figure out whether the zeros are in the left half plane or the right half plane. Okay? And of course, our implicit assumption is that the system is stable, which means all the poles are in the left half plane, or you could have a single pole at the origin which acts as an integrator for the system. So these are all the things you can actually infer from looking at the Bode plot, and that's the reason why Bode plot was so useful, because I have a very complicated system with vacuum tubes and whatnot. I just don't have an understanding of how to model these systems. So I'm not going to even think about modeling these systems. I'm going to put in a sinusoidal wave. I'm going to look at the output. I am going to plot the Bode plot, I am going to plot the magnitude plot, I am going to plot the angle plot, the phase plot, and based on this two information, I am going to infer what the approximate transfer function for that particular system looks like. And using that transfer function, I can design amplifiers or rectifiers or demodulator and things like that by picking an appropriate control system for that circuit. Okay? And this whole technique was actually developed by Bode. He made remarkable contributions in this field, and I'm sure you are happy to know that he is actually sitting in this room 100 years ago. That's all I have for today. In next class, we are going to talk about second order system and Bode plot for the second order system.